how electrophoretic mobility of a molecule is controlled by the applied field strength in terms of voltage. I gave you an explanation regarding what is the potential difference and how the distance between the two electrodes can affect the potential difference. And then we correlated how potential difference is going to have an effect on the amount of current generated during electrophoresis, and why is it essential when we talk about amount of current generated. How does it correlate with respect to the heat generated and the factors which are affecting electrophoretic mobility, how it controls all those factors, like how does it how does the amount of current getting affected by increasing voltage is going to be correlated with the amount of heat generation. It is basically because of the frictional force, as well as it is the amount of heat generated increases the concentration of the buffer ions, and hence more and more charge is actually carried by buffer ions, which lead to more amount of current, and greater the amount of current and greater the amount of friction leads to more amount of heat generation, and as more and more amount of heat is generated, it again leads up into this vicious cycle of increasing the temperature. And although increase in temperature is inversely correlated with the viscosity of the viscosity of the medium increases, which in turn also affects the friction and the temperature association. So we thought of that how can we control when we increase or when we correlate voltage with or voltage with current generation. If we can correlate voltage with current generation, and if we increase the voltage, how the current also increases and leads to all those conditions that we have discussed in the last class, how we can control it. The control can be done very easily by just application of a cooling system, so that the amount of heat generated can be controlled. And on the basis of heat control, although even if we keep the amount of current constant, the extent of heat generation can be controlled by the cooling system, and depending upon that, we can actually adjust the conditions so that we get optimal separation. So this is what we were discussing in the last class. So other factors which affect, apart from the applied field strength, is the buffer. Buffer affects the electrophoretic mobility in three different aspects. But before I go into making you understand that how buffer affects the electrophoretic mobility of the molecule, let me first ensure that whether you have got the concept of how applied field strength can affect the electrophoretic mobility of our biomolecule in different ways, not only dependent upon voltage, but current, as well as resistance in terms of the electrophoretic movement of the molecule as it leads to friction, and how the friction can lead to heat generation and changes in the media's viscosity parameters, and thereby also lead to overall increase in current and all that stuff. Is that much point clear?
Yes.
Okay. So now we will move into understanding that in what ways buffer can affect the electrophoretic mobility of the molecule. First and the foremost, the extent of charge on the molecule is essentially dependent upon the pH of the medium. And the pH of the medium is controlled by buffers. So unless we have a typical, what you can say, uh, most applicable buffer in our at our disposal, we cannot actually ascertain whether the molecule will bear a particular level of charge only and will continue to have that charge all throughout the electrophoretic separation procedure. So the pH of the buffer is the primary is of primary importance. And on what basis will you now choose the buffer? If I say that my molecule is going to have a positive charge if and is stable by bearing that positive charge at a pH of say 4, then how will you choose the buffer? What will be your consideration in order to choose the buffer? Yes, anyone? I will some background about batting anything but of and of like acid and a sodium acetate mixture. However, we say acetic acid and acetate as this is not clear. Is that now? Yes, is it clear now?
Yes, it's better.
Okay. So I'm saying that we'll have to give you a concept of buffers. And when we consider buffer, it is nothing but a solution of weak acid and its salt of strong base. Like for example, acetic acid and sodium acetate. If I mix the two things together in mostly similar molar proportions, then I will get a buffer. But that doesn't mean that it is going to give me good buffering at all the pH values. Am I making the point clear? Yes. So if I say that I have prepared a solution of acid and take its salt of strong base and mix them in equimolar proportion, that doesn't mean that this buffer will be having a good buffering capacity at every pH value. Okay. The buffer will have good buffering capacity. That means at what pH the buffer will have good buffering capacity depends upon the Henderson-Hasselbalch equation. Do you remember the Henderson-Hasselbalch equation? Which we discussed during understanding the concept of pKa in previous classes. Yes?
pKa is equals to pH.
pKa is equal to pH when the concentration of undissociated acid and dissociated acid is equal.
Yes, sir.
What that actually means, what that actually means is that when the concentration of undissociated acid and dissociated acid, now I will give you a simple concept now. Undissociated acid is nothing but weak acid concentration, and the concentration of dissociated acid is nothing but the concentration of its salt. Are you getting the point? So when these two equals, then you will get the pH is equal to pKa. That means, in short, if you want to imagine that at what pH the buffer is going to give you good buffering, you should have some understanding about the pKa of that particular weak acid. Okay, so if the pKa of the acid near to the pH range in which you want to work, then the buffer of that weak acid is going to work wonders for you. Is the thing clear? Yes? Okay. I give you another understanding, or is this fine? Okay. Understanding, like when I equal the portion of acetic acid and the sodium acetate, imagine then okay, just give me, I may then perhaps will make better. Just give me 2 minutes. It's okay. Yes, is it better now?
Yes, sir.
Yes, sir.
Okay. I will be sharing again. Okay, so we were talking about the buffer, and I gave you an understanding that how a buffer is prepared. What you need to take home message is only this: that when you're choosing a buffer, you need to consider what is the pKa value of the weak acid, and the pKa value of the weak acid is going to tell you in what pH range the buffer is going to work good for you. Is this much fine?
Yes, sir.
Okay. So considering this, we choose the buffer. The second, that means the second criteria, that means the composition of the buffer is chosen on the basis of the pH range in which your molecule is going to be stable and is going to be bearing the charge during electrophoresis. And therefore, the choice of buffer is dependent upon the molecule of your interest that you want to separate. There are a few things more apart from this, like although your molecule bears a charge, take an example like this, that although your molecule bears a charge in this particular buffer, say other component molecules from which you want to separate your molecule during electrophoresis also gain similar extent of charge, then it will not be of your then you cannot just rely on the pH of the buffer, okay, or the composition of the buffer. You will have to slightly change your buffer in such a way that now your molecule gains a unique extent of charge so that you can separate the molecule better. So buffer composition is in one way important. Also, while choosing the buffer, you should be also more interested in finding out that whether buffer components are having any kind of are going to do any kind of molecular interactions with your molecule of interest, or any components within the molecule, or within your mixture of molecules or not. Why is this important according to you? Let me say, suppose I choose a buffer. Okay, let me give you an example. Okay, uh, this kind of a study was done by Keynes in 1960s. Okay, and he was trying to separate BSA. I hope that you know what is BSA. What is it?
Bovine serum albumin.
Yes. So he was trying to separate BSA, or you can say isolate BSA from most other proteins. So what he did was that he used a borate buffer. Okay. Now the problem of borate buffer he identified a bit later. Now, when he was using borate buffer, then when he electrophoresed BSA, okay, he got first in the electrophoretic gel, he got 2 bands of BSA. Okay. Now he thought that perhaps his BSA sample, what he used for performing electrophoresis, was not very pure. So he got 2 bands. So then what he did was that he was more concerned about a darker band. So he actually purified a darker band. That means he isolated BSA from this gel. He used this darker band and he reloaded it onto the same gel and performed electrophoresis in borate buffer again. Okay, he again got 2 bands. Can you give any explanation? You got the situation, right? First, he used a BSA sample that was with him. He supposed that that BSA sample was pure enough. Okay. He subjected it to electrophoresis. He got 2 bands. So he thought that perhaps the BSA sample that he was using was not that pure. So he used one band. He purified BSA from one band and he electrophoresed it again. To his surprise, although he purified the BSA only from one band, he still got 2 bands. What could be the reason? Yes, anybody? Yes. Can you guess what could be the reason? Is the question clear, first of all? Is the question clear? Okay, am I audible?
Yes, sir.
Okay, the question is clear. So can anybody try and answer this?
Sir, because of the buffer, maybe?
Like, what could be the reason why the buffer is having this kind of an issue with your sample? Instead of getting single band, although you have isolated BSA from that single band, when you subject it to electrophoresis, again you are getting two bands. How is this possible? Obviously, because I'm describing this kind of a setup under the heading of buffer, it has to do something with buffer. But what the buffer was doing? Any guesses? Yes? Okay. No, molecules, see, if your Janki says that maybe the molecules are with different size. Obviously, if they are of different size, you are going to get two bands. Fine. But it is the same molecule, right? It's BSA. So all BSA molecules should have the same size. Yes or no? Yes. They should have the same size, but still you are getting two bands. What could be the reason? Any guesses? Obviously, he realized that there is something wrong with the buffer. So he used this same band, the BSA purified from the same band, and he electrophorested it using a different buffer other than borate. He got a single band. So now at least are you trying to uh, get to the answer? Can you get to the answer now, if I say so? Yes, anyone? Okay, I will give the answer because nobody is even trying to give the answer. Uh, what actually happens is that BSA undergoes a reaction with borate. Okay, and not all, because borate has to be taken at a particular concentration. At that concentration, only some molecules of borate partially modify BSA. And because they partially modify BSA, what you see is that the modified form of BSA migrates differently compared to unmodified form of BSA. Is this possible? First of all, at that time, obviously it was in 1960s. At that time, electrophoresis was just in its infancy, and hence it was not very clear that why certain buffers cannot be used. But later on, it was understood that like certain buffers like borate cannot be used for proteins because borate interacts with proteins, and because of that, it might modify certain protein molecules. Now, when it does so, then you will get one BSA native molecule and another molecule which will be a BSA modified by borate. Does that make sense? Now, when BSA gets modified by borate, then it migrates as a different molecule altogether. I hope that I have made the point clear. Is it clear? So from here, what I'm trying to convey is that even while choosing the composition of the buffer, you should be very certain that the buffer is not going to interact with your sample. It should be inert with respect to the sample. That means in terms of chemical reaction, it should only affect the charge status because of the pH of the buffer. On that basis, certain buffers have been commonly identified, like for example, formate, citrate, phosphate, EDTA-based buffers, acetate, pyridine, tris buffer, barbitone buffers, and so on and so forth. Such buffers are actually considered pretty well during electrophoresis. However, you can use this property of buffer, that means reactive property of buffers in certain cases for your benefit. Like, for example, if you want to work with carbohydrates, carbohydrates are essentially uncharged and cannot be separated by electrophoresis. But if you want to separate them by electrophoresis, you might make them gain charge by interaction with certain buffers. So you might deliberately choose certain buffers which are going to interact with your sample in certain cases if you are not very interested in retrieving the sample back. Am I making the point clear? Is this clear enough?
Yes, sir. Just one question. Can you tell
Yes. Go ahead.
when BSA and borate were present together, what charge was BSA carrying?
BSA was carrying a positive charge.
Okay, then it makes sense that BSA and borate got uh, um, together in some interaction, and a modified BSA was formed with a native BSA.
Yes.
Also, because borate in itself doesn't releases H plus ions, or boric acid doesn't in itself releases H plus ions, but takes them from the water and uh, takes up the OH of the.
Obviously, see, one thing, Bhavika, has to be very clear in your mind. Whenever you are choosing any component for formation of buffer, that essentially should be a molecule which doesn't liberate protons very easily. That means it should be a very weak acid. Then only it can work better for you. Does that make sense?
Yes, sir, but in case of borate, it doesn't releases its H plus in any condition. It takes it the H plus it releases, it is of water, and it takes
Obviously,
OH
it
of.
is actually going to interact in some or the other way so that it can behave like an acid, right?
Yes, sir.
Obviously, when we are considering borate as boric acid, it, we are naming it as an acid, then it has to have some way by the way of which it can liberate protons, correct?
Yes, I was just trying to highlight the difference of the weak acid like acetic acid and weak acid like boric acid.
Right, obviously, yes. So, anything apart from that you want to ask?
No, sir. Rest.
Okay, good enough. So interestingly, now whatever be the reason, interestingly, you can sometimes use such different kind of buffers which can interact with your sample molecule for your utility. Okay, and the examples is of say carbohydrates which cannot be otherwise electrophoresed because of their essential neutral nature. In sometimes you can make them interact with certain buffers or certain specific buffer like molecules in order to make them gain a charge. And when they gain the charge, then you can very easily separate them by electrophoresis. The only thing or the point of caution here is that you should not be interested in the molecule after separation. Okay, because if you want the separated molecule to be purified later, then it will be of no use because it has already undergone chemical modification. So first of all, how do you choose the buffer? That I have made pretty clear, I believe, on what basis you choose the buffer. And two, it should be non-interacting. Three, it should also you should also consider the ionic strength of the buffer to be an important factor while you are choosing the buffer. Like those buffers which can work or which can bring about good buffering even at low ionic strength can work good for you during electrophoresis. However, those buffers which can work only at higher ionic strength, they cannot work well for you during electrophoresis. What do you think? Why? What could be the reason for this? Yes, the reason is given over here. If you read it carefully, if those buffers which can work only at ionic strength are used by you during electrophoresis, the problem that you are going to face is that major portion of the current will be carried. That means the charge will be carried essentially by buffer ions. Okay, I explained it to you that why this happens. So in the last class, I gave you a kind of situation. The reason is that when you compare the size of buffer ions is, say, suppose this, and the size of your sample is this. Okay, although they might carry same charge, the situation is the density of the charge is more on buffer ions. And also because they are small, they can move quite easily because separation during electrophoresis is essentially based upon charge to mass ratio, right? So more the charge and less the mass, more movement will happen during electrophoresis. That is why buffer ions, if you use them at higher concentration, the problem is that buffer ions will continue to carry more and more amount of charge, and your sample ions will not get a chance to carry the charge, essentially the charge. That means your sample ion mobility will be reduced drastically because of this process. And you will get more amount of current that will lead to all the sorts of problems that we have already talked about. Is this much clear? So while choosing the buffer, one has to be very certain that your buffer should work at a proportionately good ionic strength value as well. You cannot just use any buffer that will work only at higher ionic strength. So higher the ionic strength, higher will be the charge, and more problems that you might start to face. Okay. So, and pH, we have already decided that we have already talked about this, that the pH is another controlling element in buffer. So while choosing buffer, you need to be very, very clear about these three aspects of the buffer while choosing it. Is this fine enough? Should we move ahead with another factor that can control electrophoretic mobility? Yes. The last factor that controls electrophoretic mobility of the molecule is the medium. Now, we will talk about this slightly later on in greater detail, but for that you need to have an understanding that what exactly does this medium means during electrophoresis. Medium is the environment in which you are carrying out electrophoresis, one. However, you can supplement it with certain things, like for example, when you carry out electrophoresis in gel, the separation is better. Okay. However, you can use other medium as well. You can now, instead of calling it as medium, it is better to call it as support medium. Okay. So that's why the term here is used. This is supporting medium. This is not actually going to be causing a very, what you can say, substantial change during electrophoresis, but it enhances the extent of resolution that you're going to get during electrophoresis. That's what the purpose of electrophoresis is. You should get essentially good separation, right? And you can do it by using certain inert support medium. Now, although we say inert, there are certain support media that interact with your molecule as well. And that interaction can sometimes be used for your benefit. Like for example, One support medium is paper. So when you're using paper as the support medium, is not essentially inert, right? I hope that you might have studied something about the properties of paper during chromatography, right? Essentially, what is paper chemically?
Cellulose.
Yes, it's cellulose. And what's the property of cellulose? Which is used exactly during chromatography. What's that property?
Water holding capacity of cellulose.
Yes, yes. It's basically, and how does it hold water? On what basis it holds water? Holds water because of its adsorption power. It's not absorption, it's adsorption. This is a surface phenomenon. Now, when we are talking about adsorption of water on paper, it is something like if I draw paper like cellulose fibers like this, then water is held on to paper, water molecules are held on to paper and they are not allowed to move. Okay. Now this becomes slightly more problematic here in case of electrophoresis. In chromatography, you can use it for the purpose because there is no other force which is driving the solvent anywhere. However, during electrophoresis, what is happening is that some portion of the solvent is always associated with the ions, as we know. They form the hydration shell around the ions, right? Do you remember that? We talked about this in previous classes, right? So if there is a charged entity, then the charged entity around it has a solvation shell, right? And that is done by water molecules. So if certain water molecules are held onto paper and they were a part of solvation shell, what will happen to your charged entity? What do you think? What will happen?
It will also not move.
Yes, it will be retarded. It because to be more precise, it will be slightly held to the paper. It will continuously be held onto paper. Just imagine something which is something like a ball is moving, okay, with all the water molecules at the periphery, and there is a paper below it. So certain water molecules will stick onto paper, retarding the movement of this ball further, right? And this will continue over and over again. You are getting the point, right? Although essentially, because of the charge on the ion, it will be pulled towards one end of the electrophoretic unit because of the charge. So essentially, there will be a force dragging that molecule. You can consider it like that, instead of the molecule moving smoothly all throughout. So there will be more amount of dragging that you will see. So essentially, when you carry out paper electrophoresis, then instead of getting sharp separation bands, imagine now this is the paper in which I am carrying out electrophoresis. Instead of getting sharp bands, what you get is something like a comet with a tail. And that is because some molecules are retarded while some molecules continue to move. So will this be of your choice in order to bring about good separation? Is the question clear? Obviously not, but imagine that this can work better for you only if the molecules that you're separating are far different from each other. Like you were getting two bands this separate in usual situation, So if it is dragged during electrophoresis, you will get two bands like this. Okay. Rather than bands, you will get spots. Okay. However, if two molecules are very similar to each other, just they differ by just a minor value, then separation by doing paper electrophoresis will be useless. Are you getting the point? So obviously, the type of the medium that you are using matters quite well, but you will understand that why to use a medium. Can anybody guess if this is the problem that a support medium can cause? Why to use a medium after all? Why do you need a medium for carrying out electrophoresis? Is this not a valid question to ask? If incorporation of a medium is going to cause certain problems to you, then why will you ever use medium or incorporate use of medium during electrophoresis? Do you think that this is valid to ask? Yes? Yes, it seems that it is valid to ask, right? There has to be certain distinct advantage of using medium. Okay, it could reduce mixing of the sample. What do you mean by that, Janki? During electrophoresis, each sample molecules are going to gain a different charge and are going to migrate with a different speed altogether. So is mixing of the sample really going to be your point of concern? If I may add, it's actually
So
going to
medium,
affect.
so that
Yes, yes.
mediums there should be some resistance at all, so that our sample which we are trying to separate just doesn't directly reach to the electrode and get destroyed
Okay,
or electrolyzed.
okay. So do you essentially need a medium for that?
To
I
create
mean, you're trying to say that in some or the other way, the medium is helping retardation of movement of your sample molecules, and because of that, you will use medium. Am I putting it correctly?
yes, so retardation to some extent, not to this extent that it doesn't even moves properly and there is not a proper separation, but retardation to some extent is also necessary. We cannot let it
Okay,
fly. Like some resistance is also necessary. If we decrease
okay.
the resistance altogether, then we saw that how there could be a problem uh, with a lot of current being generated and also electrolyzed sample.
Mhm. Okay, that could be one point of concern, but there are certain other things that you will slowly understand. Okay, I will come back to this question, however, and if I forget coming back to this question, then please remind me of doing it. Okay, I'm not answering it right now because you need to understand certain intricacies about electrophoresis first. Okay, let us first understand that how electrophoresis developed as a technique for separation of molecules. Essentially, there were two forms of electrophoresis in which it was developed. First was called as free electrophoresis, and the other one was called as zone electrophoresis. The basic difference between the two is that in free electrophoresis, you don't use any stabilizing media. So it is without any stabilizing media. You carry it out just in buffer. Okay. While zone electrophoresis is that you in which you incorporate a stabilizing medium. Okay. So this much is clear. What is the difference between free electrophoresis and zone electrophoresis? Yes. Okay. So now let us first consider that how free electrophoresis. Now this has only you can say historical importance, understanding free electrophoresis, there were two forms of free electrophoresis that were developed. One is called as microelectrophoresis, and the other one is called as moving boundary electrophoresis. I will briefly tell you what microelectrophoresis does. Okay, and then we will go to the understanding of moving boundary, because moving boundary electrophoresis essentially raised certain concerns which are responsible for which were responsible for development of zone electrophoresis. Okay, so first of all, let us understand what microelectrophoresis looks like. Microelectrophoresis apparatus was developed by Abramson, and this is called as microelectrophoretic cell. What was there was that in between here, there was a vessel, you can consider, which was just like two glass slides placed one over the other, just like that. Okay. There was a small gap in between the two, where your samples were allowed to undergo electrophoresis. So there were two electrodes connected at two ends. You can see these are the two electrodes which are emerging out. And this is the portion from where the buffer is allowed to be free flowing all throughout. Okay, you can add buffer from here, and the buffer was free flowing, allowed to free flow all throughout, so that you can get a continuous supply of buffer from here, which will be moving from here to here to the two electrodes. The arrangement is understood? Yes? Is there any problem in the arrangement? Now, in between the gap between the two, now this is just an oversimplified version of it. In between the gap between the two glass slides was placed your sample, whichever you want to whichever sample you want to electrophorese. Okay, and what you used to do next was that the movement of the samples were observed under by using a microscope. So this entire assembly was placed under a microscope. Are you getting the point? But electrodes are allowed to get inside. Bhavika is asking that why the electrode placement is like that is not clear. This is very old arrangement, and is actually used for separation of certain cellular components. And why it is used for that also I will delve upon. But basically, the electrodes go inside this assembly just like this. Okay, the electrode is like this, so that you can connect it to a power supply outside the cell, and the what you can say, the buffer is allowed to move inside, so it gets into the buffer, the electrodes get into the buffer here, and in between these two electrodes, this entire area is connected by means of the channel that is created by buffer. Is this much clear? Okay, fine. So now what happens is you observe the movement of the cells that is happening under the effect of electric field by using a microscope. Why will you be ever interested in finding out how the small particles move under the effect of electric field by using a microscope? Something like cells, like RBCs or bacterial cells. Why should you be interested in observing mobility of cells under the effect of electric field? Okay, I will give you the answer. The reason is, this is actually done to find out what is called as zeta potential. Have you heard about this term previously? Zeta potential. Yes, anybody has heard this term previously, zeta potential? Okay. This plays a very important role in very important property that is associated by, okay, Janki says yes. What do you mean by zeta potential, Janki? Can you elaborate? Yes. Okay, I will give you a reason for this, why you are interested in estimating the zeta potential. Have you ever imagined this previously? RBCs are present in blood, right? Okay, so just imagine that this is the blood vessel and RBCs are moving along with the blood flow. Okay. It is the charge will develop at the interface between solid surface and liquid medium. Partly correct, Janki, but I'm explaining why you are interested in finding out zeta potential first. Okay. So now just imagine that RBCs are moving along with the blood flow. Okay. Have you seen a water stream moving? Anything that is suspended in a water stream, just like during the movement of river, if there are certain particles which are suspended in the water stream, what happens to those particles as the stream moves? Yes, anybody? In water, if there are certain suspended particles, if you set it in motion, that means water is set into motion, like a stream of water, what happens to those particles? They don't move with the flow, Bhavika. Flowing water is always considered to be pure, right? In the sense that it doesn't carry impurities unless you disturb the flow by some or the other way. It actually settles. It allows settling of the particles, right? If you set it in motion, the particles tend to settle down during the movement. They move to a certain distance, but they settle down eventually. Yes or no? Bhavika? Yes. So now have you imagined this previously, that blood is continuously moving, right? With its suspended things in it, like RBCs are suspended in blood. Why don't they settle somewhere? They cannot settle at the pump, meaning obviously at the heart they cannot settle. But once they are set into motion, when the blood is moving continuously through the capillaries and through the blood vessels, is it not a thing to ask that why don't these RBCs settle during when the blood is in motion? Because these are suspended components, right? In blood, they don't dissolve in blood, correct? If you keep it standing for some point of time, you might have seen this, like when you draw out blood, if you keep it standing for some time, RBCs settle down all by themselves, correct? Then why in motion they don't settle? Have you ever imagined this? It is because of the zeta potential. Okay. Because every blood cell has a particular what you can say membrane potential, and because of that it is considered that the cell on its surface is comparatively negatively charged. Yes, who is this? Wants to say something? Yes, Vikas wants to say something. Vikas? Okay, fine. So now on the surface, if RBCs are negatively charged, their zeta potential is calculated by means of what is the potential difference between a layer of water which is immediately in contact with these charged surfaces compared to the water molecules which are far distant but are still vaguely associated with this charge. Does that make sense somewhere? So in short, what is it is like some water molecules will be held tightly onto the surface of any charged entity, while as you move away from here, from this surface, the water molecules will get loose and loosely associated with the surface, right? So in one way, what Janki was saying is correct. It is the potential difference between those molecules which are closely associated compared to those molecules which are in motion. This difference. Why this is important is because just imagine this, and there is another entity which is having the same negative charge on its surface. It will also have some water molecules held tightly here, while as they move ahead or as they move away from the surface, they will be loosely bound, right? So what this does is that these water molecules which are in between, which are loosely bound, are comparatively more mobile compared to those water molecules which are held on the surface. Does that make sense? What basically this is doing is that this is keeping the two cells far apart from each other instead of allowing them to come very close. So in short, it is a kind of a repulsive force between similarly charged entities, which don't allow them to collect together at one particular point, rather than they are kept far apart from each other because of this repulsive force. Okay, I have tried to simplify what is meant by zeta potential, but have I made the point clear enough in order to understand that what is zeta potential? Okay, so what I will do is that I will stop here today because it's almost time. The movement of RBCs, if you look under a microscope, can give you an idea how fast it is moving from one point to other. It can give you an idea about the zeta potential of RBCs. And on that basis, you can decide that whether the RBCs you are looking at are healthy or towards the end of their life cycle. Okay. And on that basis, you can actually count how many RBCs are healthy and what's the proportion of healthy RBCs with respect to those which are dying. That can give you a prediction about that whether your system is properly involved in blood cell production or not, and so on and so forth. It was a very relative and very tedious way of calculating it. Nowadays, it has become much more easy, but it was at that time during 1930s or so. This was the understanding about the zeta potential, or this was the way in which the zeta potential was measured. So remember this for some point of time. This is just the first ever way in which electrophoresis was carried out. And at that time, because you were actually tracking the movement of charged entities uh, between two points within the cell, that was referred to as microelectrophoresis because you are actually visualizing it under a microscope. So that was the concept of microelectrophoresis for you. We will discuss something about moving boundary electrophoresis, okay, in our next class. So that is it for today. In case you want to ask any questions, then I'm ready to answer. If there are any questions, I can answer